Welcome to the seventh set of presentations in the second webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We hope that all of our attendees, their families, and their colleagues are safe amid the ongoing COVID-19 pandemic. We thank everyone for attending the webinar today. The webinar series, which began in the spring of 2020 and then restarted last autumn, has been an immense success, and the recordings of those webinars continue to be viewed on YouTube. We plan to continue these webinars through the present academic year with a variety of speakers from industry, academia, and other research institutes, as well as PhD students and early career researchers. Subsequent webinars will be announced on the IAS mailing list and the IAS Twitter feed. Today's webinar will be given by Nicholas Carente and Shivan Parashar, PhD students at Rutgers University, and Klaus Richard, a PhD student at Universidade Federal do Ceará. These students were Best Poster Award recipients at the inaugural IAS Twitter Poster Conference. I am Nicholas Wilkins at the University of Alberta and the IAS Student Education Committee. Today's webinar will be moderated by David Donacci of Imperial College London in the United Kingdom. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you have not already. Our dues are minimal, only $20 US per year to support the publication of our flagship journal, Adsorption, contribute to travel grants and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter at @intadsos for future updates regarding IAS events, webinars, and information about scientific meetings. Please help expand our YouTube channel by subscribing. We would like to remind the viewers of the upcoming Fundamentals of Adsorption Conference in Broomfield, Colorado, between May 22nd and 27th, 2022. More information can be found on the website given in the slide. The presentations given in today's webinar are by the recipients of the Best Poster Award in the inaugural IAS Twitter Poster Conference, which was held between the 7th and 11th of December 2020. The 5 recipients were chosen by a committee of judges, most of which are members of the IAS Education Committee. All 5 recipients were invited and have agreed to give talks in the July and August webinars. The awards were funded by the IAS and the Georgia Tech Separation Center. And now I'll hand it off to David to introduce our first speaker today.
Klaus Richard is a PhD student in chemical engineering at Universidade Federal do Ceará in Fortaleza, Brazil. He expects to graduate in December 2023. Klaus is supervised by Dr. Moises Bastos Neto and Dr. Diana Azevedo. Klaus completed his bachelor's degree in chemical engineering also at Universidade Federal do Ceará in 2018, and then rejoined to do his Masters of Science in Chemical Engineering, which he completed in 2020. His research interests include general modeling and simulation for chemical engineering and adsorption processes, statistical modeling and machine learning, molecular simulation, and computational fluid dynamics. With that, I'd like to welcome Klaus to give his presentation.
Okay, so thank you, Nicholas and David. So my name is Klaus, and I will present from this webinar the topic of evaluation of intraparticle mass transfer properties by microcalorimetry. So this project had many contributions. I put them all here. They are all my colleagues for LPACO2. This is the same laboratory. And then I'll start the presentation now. So a quick summary of what's going to be presented here. I will divide the presentation introduction, objectives, the methodology, results, and conclusions. Starting with the introduction. For the purposes of this presentation, it's possible to divide adsorption into two big areas. So there is the equilibrium. So there is the equilibrium, which deals mostly with the total capacity of an adsorbent, which is related to a lot of properties such as surface area, and then the kinetics of adsorption. This is more interested in velocity and time. So in this presentation, it's going to be dealt with the kinetics of adsorption. So why it's important to study the kinetics of adsorption? Because if we're trying to separate two components in the same adsorbent, here this graph shows that if we wait until equilibrium is reached, both components 1 and 2 have similar adsorbent concentrations. So the separation won't be as effective. But if the process is stopped in earlier times, the separation is much more efficient. So this is one of the reasons why it's important to study the kinetics of adsorption. And the most classical way of representing how the mass transfer process of adsorption happens is through diffusion. And this is the form of Fick's law. And the interest to describe the adsorption of a component, the kinetics of adsorptions, is the diffusivity parameter. So this is the whole thing that will be tried to determine in this method of measurement, of estimation. So there are already many methods of estimation of diffusion. So some of them are gravimetric methods that correlates diffusivity with rates of adsorbed mass change, piezometric methods which correlate it with pressure change, chromatographic methods which correlate it with concentration change, and this new microcalorimetric method that correlates diffusivity with the rate of heat transfer change. So this is the new method that's going to be discussed in this presentation. And why, if there's already many methods out there, the microcalorimetric is a useful method or a novel method to put here. So microcalorimetry is already used to obtain equilibrium properties like adsorption isotherms and enthalpies of adsorption. So in a single experiment, once it's also possible to determine the kinetics of adsorption, it's possible to determine 3 parameters, both of equilibrium and kinetics, in a single experiment, which is very convenient for saving time and having, in general, a very experiment that can determine a lot of physical information about a process. So now that this is introduced, let's talk about the objectives of this method in specific. So it's to propose it and to derive a mathematical model suited for the estimation of the parameters. This is going to be a mathematical model to couple with the experiments to determine the diffusivity and evaluate how good the method is. Is that simple. The methodology, we start with talking about microcalorimetry. It's a field dedicated to study heat transfer. This is the same as normal calorimetry, but the monitoring is done with high sensitivity. The equipment used has a high sensitivity to heat transfer. So it can measure low amounts of mass and low amounts of heat transfer. So it's good for that studying adsorption for that reason. And so a quick explanation of what's happening inside this equipment is there is a cell. And inside this cell, the adsorptor will be introduced, and here is the adsorbent. So once the adsorptor is introduced, heat's gonna be generated, and these lines, they represent thermopiles, which are thermoelectric materials that transform a gradient of temperature into a gradient of potential, which means that they can measure the heat transfer between the walls of the cell and the calorimeter and output it in a computer. So this is basically what happens once the adsorptor enters the cell. And the response of this experiment that happens is the microcalorimetry curve, which shows the heat rate of or how much heat is transferred to the walls of the calorimeter per time. So this is what's gonna be evaluated for the calculation of the diffusivity. And here is a drawing dividing and explaining how the experiment is done. So this first red dashed part of the equipment is called the vessel. The vessel deals with measurements and introducing the amount of gas that's going to be introduced in the cell. So we set a pressure in the pressure transducers, and this valve 7 opens, and then the gas flows through a dead volume, which is represented by VD, and enters the calorimeter sample cell, which is where the adsorption will actually happen. And so the principle of measurement of the diffusivity is that the rate of energy generation is proportional to the rate of mass transfer. So the faster heat is transferred, the faster the mass transfer is. And so through the peaks, it can be seen that a fast diffusion will have a peaks with high amplitude and short duration time. And the slow diffusions will have a peaks with low amplitudes and long duration times. So this is how in a without any calculation that we can see how is the diffusion fast or slow, relatively speaking. And so the first step to actually estimate the diffusion is to calculate all the equilibrium properties. So through the peak, it's possible to see that once the equilibrium is reached, no more heat is transferred. So the first equilibrium point is at this point here where there is no heat rate. And the second equilibrium point is where this peak stabilizes. So we can identify the equilibrium is reached through this peak. And by the area below the curve is the total heat transfer, which will be a compound of many heat transfer resistance. And the total heat is going to include the heat of adsorption plus here in this case of these equipment, the increase of temperature by the compression of the gas, because the pressure inside the cell will raise because new gas is being introduced. The volume is constant. So after that, it's necessary to determine the isotherm. And so there is a pressure transducer equipped in the whole experiment that can be used to determine what is the equilibrium pressure. So by multiple introductions of gas, raising the pressure in different runs of the experiment, it's possible to obtain the isotherm. So with these two equilibrium properties determined, we can move on for the diffusion estimation. So here, this is the same picture shown before, and this is these highlighted domains are the simulation domains, the model domains, the vessel, the dead volume, and the cell. So they will be described mathematically. This is the part of the modeling now that we are speaking. And so the assumptions very quickly, since the pressure is low, assume the ideal gas equation of state is valid. The solid and the gas are considered in thermal equilibrium. External mass transfer on the adsorptor are negligible, and the pressure of the transfer line, which is the dead volume, is equal to the cell pressure at any time. And the heat is transferred to the cell wall occurs only in the radial coordinate. So this is the simplifications of the model. And so there's a very simple mass balance that's going to be in the vessel, in the dead volume, and in the cell. I can talk about more than later. And discussing about the heat transfer, since the heat is going to be generated inside the cell, it will transfer through convection to the walls of the calorimeter and will be transferred to conduction to the transducers that will actually measure the heat transfer, the temperature measurement. And so the energy balance are described by these three equations, which will include all of the resistance of heat and all the process of heat that happen inside the calorimeter. And these are the unsteady state conduction equations through the walls of the calorimeter that will be finally used to correlate this with the diffusivity. So here talking about the pressure profile of the calorimeter, since the vessel is lowering the pressure and the cell which is receiving the gas is going to raise the pressure, at some moments they will equalize. And the way to describe this is only necessary to determine only one of the pressures, either the cell pressure or the dosing vessel pressure, is an exponential pressure, an exponential equation, which can be determined experimentally since the pressure is being measured at all times. And so this is the kinetic model of adsorption. It's also possible to model the same experiment through desorption. And it's the same process, but the process starts inside the cell. So the cell is saturated first, so the gas enters here and equilibrium is reached. And to actually measure the diffusion, this valve is open and the flow is in the reverse direction. What this means is that for modeling purposes, the vessel is not important anymore because of the initial conditions are all in the cell and in the volume and the dead volume, because they are all connected to each other. So it doesn't matter what happens for the mathematical model, what happens in the cell. So this simplifies the model, and the calorimeter peaks is inverted because the temperature will be decreasing because of the desorption. And the model will just be two equations, one for the cell and one for the dead volume. And the energy balances are the same equation, but without the vessel. The adsorption models are these three that we used in our work. And most of the time, it's only these two, which this model deals with intracrystalline diffusion, which is only one resistance, and this when there are more resistance included. And so the final way of where the diffusion parameter will be estimated is through optimization of the parameter. The microcalorimetric peak will be modeled through this equation, which is the conduction equation through the walls of the calorimeter, and the parameter that fits the model curve with the experimental curve will be determining the diffusivity. And the results here for this model, first we have to gauge what the model is capable of doing. So to actually measure the diffusivity, it's necessary that the intraparticle resistance is bigger, or at least significant, in relationship with the other resistors, such as reach transfer resistance and the rate of pressure decrease, which is the valve restriction. So these reports of Brandani show that a valve, how much restricted it is, work as an additional resistance. So here, this alpha shows how free the valve is. So this value shows that the valve is fully open, shows how sensitive the model is for each diffusivity parameter. So it's not possible to see much here because the curve in its complete form has many contributions of heat transfer resistance. So by zooming in the initial parts of the curve, which shows where the adsorption is more relevant, it's possible to see that the less higher the diffusivity parameter is, which means the bigger the mass transfer resistance is, the better is the sensitivity of the model. So once it reaches 0.05 in the diffusing parameter, it's not sensible anymore. So this shows a limit of what diffusivity can be measured in this. And once the valve is being more restricted, now with 30 as the coefficient, it becomes less and less sensitive. Now it's less sensitive here, which about 0.01 is the max measurement. And when the valve is very, very restricted, and it's almost not sensitive above 0.01 in the effective diffusivity parameter. So it's necessary that the valve restriction is as low as possible to actually employ this method. And talking about the effects of convective heat transfer, it's not possible to eliminate it. Any single value of the heat resistance, either it be very high or very low, it's going to affect the microcalorimetric peak. So it's necessary to measure it every single experiment for every single adsorptive type. And so the results finally for a system of zeolite 13X and CO2 shows for different pressures, a diffusivity parameter of 8.82 the power of -4. For multiple pressures, this value remains mostly constant since the pressures are low enough. And the sensitivity of the model, which will show if the parameters actually be measured, is actually pretty relevant. We can see here that our value, which is the red line, which is was the actual estimation value, is about the middle here. And if we lower the parameters, it will be significantly off the experimental curve. And if we raise the parameter too much, it will be significantly off the experimental curve in the opposite side. So the actual estimation here, it's about 8.5 to 1, the power of 4 and the power of -3, sorry, seconds. So this is the actual estimated result. And when we compare these results to many literature results, we can see that our result, which is the 8.9 here, is very close to many other results of literature in the same order of magnitude. And the next point here is to determine which mass transfer resistance is the more relevant. Either is micropore or macropore, but in this case, I show that it's actually the same level of order of magnitude. So the conclusion is that the parametric analysis of the model shows that it can actually measure diffusion through heat. The valve restriction should be as low as possible to actually employ the model. It's not possible to remove convective heat transfer effects from the response curve. And the sensitivity analysis has to be done every single time to ensure that the calculations is in the bounds to yield a diffusivity parameter. And so here, the zeolite 13X comparison with the literature was successful, and the future works may include tests with slow diffusing species such as hydrocarbons, because here we tested CO2, which is a relatively fast diffusion species, so it has a little bit of problems in measurement, but it nonetheless was successful. So the full article, which has all the parameters and in-depth explanation of the model, is this one, Assessing Mass Transfer Rates in Porous Adsorption, which was published in the Chemical Engineering Science, which can be seen if anyone's interested. And so the acknowledgements for the funding is made by the Petrobras and CAPES, and I thank you very much, all my colleagues of LPA-CO2 for helping me and for contributing a lot to this multiple contribution work. And so these are the list of references. I can go back here if anyone is interested, and now questions and additional questions can be sent to this email. Thank you very much.
Thank you very much, Klaus, for your nice presentation. We have a question that's come through on Zoom from Benjamin, and they say, very interesting work. Is the temperature dependency of the diffusivity and adsorption equilibrium taken into account in the model?
Okay, so here the equipment has a heat well, so it maintains the temperature constant. So the temperature is 298, which I believe it's employed here. and it's maintained constant throughout the experiments. So this temperature will be remaining constant, so the model can be seen as an isothermal model for the diffusion.
Right, and one of your assumptions earlier was that the gas and the solid are always the same temperature. Right.
It's because it's one thing to be noted here is that it's not actually isothermal, because it can't be, the model can't output heat transfer if the temperature is constant, because the heat is going to be in a gradient of temperature. But the temperature gradient is very small. That in the experiments, the temperature goes from 298 to 299. So this is the little amount of heat that's actually described in the experiment. So the model is not actually isothermal, but since the temperature change is very small, we can assume that the diffusivity dependence of temperature in this case is negligible.
Thank you very much. Benjamin's second question, which also Nicholas Wilkins was asking about, is it possible to differentiate between the different kinds of mass transfer mechanisms? So macropore versus micropore versus surface diffusion.
Yeah, it is possible indeed, because in this initial version of the model, we considered a global diffusivity parameter, but additional experiments have to be done to see if what's the dominating effect of if it's micropore or macropore. And so it will need additional experiments, but it can be done in the same equipment, in employing the appropriate models to differentiate between macropore and micropore diffusions.
Great, thank you very much. We have probably the last question from Zoom, from Rob Brew. Sorry if that's not how you pronounce your name. He says, or they say, there appears to be no consideration of the calorimeter dynamics on the shape of the heat flow curve. For a particular instrument that he mentioned, the time constant is very large, which then impacts the peak shape. Can you make any comments about this for your model and equipment?
Okay, so
and
the
also, oh, sorry to interrupt. And to add a related thing from me on that is, how does the thermal conductivity of the adsorbent also influence the shape of the heat curve?
Okay, so this is a very interesting question. So I'm going to be back here at about this. So here I talked about the effect of the conductive heat transfer. So in the experiments, it's necessary to do a blank experiment. So an experiment without any adsorbent, or with the adsorbent, but in inert gas like helium. This is the experiment that we do before running the diffusion experiment. So once we put, let's say, the zeolite inside the microcalorimetry, we will do a experiment of helium to see how quickly is the convection and the conduction happening inside the calorimeter, because there will be no adsorption. So there will be a system of heat resistance, like an electrical system, which will start with convection and then go through conduction in the calorimeter walls. So the dominant effect in this circuit will be the highest heat resistance. In our case, the highest heat resistance was the convective resistance. The thermal conductivity of the adsorbent and the metals that compound the calorimeter, which are all metals, are much bigger than the convective constant, which means that the dominant effect is the convection. So we can effectively ignore, or basically say that the dominant effect of heat transfer conduction is convection. But in the equations, I will go back, the heat equations on the cells, we actually consider the conductivities of the cell walls and this. But once we actually put into the model, this value is too big. So it's almost no resistance compared to convective resistance. So the most effect here will be the balance between how quickly the heat is generated and how quickly it gets transmitted into the calorimeter. And so it's interesting for this heat transfer resistance to be as low as possible. And so it's not possible really to control this, but in our experiments, the resistance was low enough so that the heat transfer from diffusion was the dominant effect of the experiment.
Okay, thank you very much for your answers to those questions, and also again for your presentation. With that, I'd also like to thank the other speakers, Nicholas and Shivam, and I'll now hand back to Nicholas Wilkins, who will wrap up the session and give some information on the upcoming webinar.
Right. Thank you, Nicholas, Shivam, and Klaus for your presentations. We also thank all of our attendees for joining this webinar. We hope it was both educational and enjoyable. An edited version of this webinar will be posted to the IAS YouTube channel with an announcement on the IAS Twitter feed. The hope is that the work discussed today will be a useful resource for the absorption science community in the future. The next IAS webinar will be given by Hideki Tanaka in September. Announcements regarding the upcoming webinar and other IAS online events will be posted on our Twitter feed and throughout the IAS and through the IAS mailing list. We hope that you will join us. Thank you.